Okay, let's begin. Yeah. So, so for today's class, I'll be helping you guys understand the concept of atomic physics and radioactivity specifically. So I'll first start with the structure of an atom. So the structure of an atom for your grade, that is IGCSE, is very simple. Please remember, just understand that the structure of an atom is such that the electrons revolve around a positively charged dense center called as a nucleus, which consists of two bodies or two types of bodies, which are or elementary particles as they are called, which are held together by a very strong force called as a strong nuclear force. These two particles are the proton and the or elementary particles are the proton and the neutron. The electrons revolve around this said nucleus in fixed orbital. Although when you go to higher grades, you will understand that the orbital is not fixed. For now, just remember that you can say that the electron revolves around this positively charged, dense, concentrated center called the nucleus in fixed orbital. The protons and the neutrons, which are the elementary particles the nucleus is made up of, are held together or bound together by a strong nuclear force, while the protons and the electrons, which are oppositely charged and have a weak electrostatic attractive force towards each other, are kept away from each other by a weak nuclear force. So here's a comparison of the proton, neutron, and the electron in terms of mass and charge. Please understand this. Proton, neutron, and electron. So in terms of mass, if you assume the proton to be one atomic mass unit noted by 1U, a neutron is almost similar, 1U. If you want me to be specific, proton is actually 1.007276U, whereas a neutron is 1.008665U, although these differences do not matter for you at your grade. So proton and neutron have the same mass, whereas an electron is much, much, much smaller when compared to that of a proton and a neutron. In terms of charge, that is Q, a proton is positively charged. If you guys remember from my previous videos, I've explained that the unit of charge is E when it comes to protons and electrons. E value is 1.6 into 10 to the power of minus 19 coulomb. The value of a proton is plus 1E, whereas that of an electron is the same magnitude, but the exact opposite charge, which is minus 1E. Whereas a neutron is electrically neutral, having 0 coulomb as its charge. Please remember, this is basically the comparison of proton, neutron, and electron in terms of mass and in terms of charge. Again, the stable structure of an atom is such that the densely concentrated center, which is the nucleus, which consists of protons and neutrons, is the center around which electrons revolve in fixed orbitals. Again, proton and neutron held together by a strong nuclear force. Proton and electron held away from each other or kept away from each other by a weak nuclear force. Next. Again, this is the comparison of the same. Protons and neutrons, yes, I did forget to mention. Protons and neutrons are together called the nucleons because they make up the nucleus. By comparison, proton and neutron are about 1,800 times much heavier than that of an electron in terms of mass. Next, we identify elements by their atomic number and their atomic mass. The atomic number is also sometimes called the proton number. I'll help you understand what significance the atomic number and the atomic mass have. So if you have an element here, for example, lithium, with its atomic mass or mass number 7, which is also called its nuclear number, and its atomic number 3, which is also called its proton number, it's obvious. You can find out the number of protons as nothing but its atomic number, Z. So number of protons is its atomic number, Z. The number of neutrons is its atomic mass, A, minus the atomic number, Z, where A represents the total number of protons plus the number of neutrons or the nucleons, basically, which is why, again, yes, it's also called the nucleon number. And the number of electrons in, if assuming that it is not in its ionic state, will be equal to the number of protons as well. Yes, this is it. Next, what are isotopes? Please remember, isotopes are nuclei of the same element which have the exact same atomic number but different atomic mass. Simple examples include hydrogen with two variations H11, H21. In fact, a tritium also exists, H31. If you notice, all these three are exactly atoms of hydrogen. They have the same atomic number but different atomic mass, or same number of protons, different number of neutrons, as you can evidently see. These nuclei are called isotopes. Next, let's talk about radiation. So you need to understand and explain radiation in a very simple, uncomplicated manner. Let me help you do that. So radiation or radioactive decay is the process of spontaneous disintegration of an unstable nucleus by the emission of matter or actually I think or is a better word, or energy. And this process is, again, like I said, radioactive decay. It is a spontaneous disintegration of an unstable nucleus along with or accompanied by the emission of matter and or energy. This is, in simple terms, a radioactive decay. So please remember this. We have discussed what isotopes are. Now, let's understand the three types of radioactive emissions. The three types of radioactive emissions include alpha, beta, and gamma radiations. So here's a comparison between alpha, beta, gamma in terms of their penetrative power. So we will continue to look at alpha, beta, gamma in all the three ways. So before that, let's take a quick break. Okay, let's continue. So we were about to compare alpha, beta, gamma radiations. Let's understand. So the type of radiations here we're comparing are strictly alpha, beta, and gamma. As evidently you can see, alpha is also accompanied by alpha particles, the alpha emission. Beta emission is accompanied by beta particles, whereas gamma rays are pure energy rays, which are in the electromagnetic spectrum. So let's compare, or let's understand what alpha particles are. Alpha particles are strictly made up of two protons, two neutrons, giving them the atomic mass of 2 plus 2, which is 4, and the atomic number, which is 2. Or in other words, they are the equivalent of a helium nucleus, He4, 2. Now, again, since they're made up of two protons and two neutrons, the relative charge is plus 2e, which is contributed entirely only by the proton, since the neutron is electrically neutral and not capable of dealing any charge. Next comes the beta particles. A beta particle is basically an electron along with the emission of an other elementary particle, which you do not discuss in greater. It is called the antineutrino. So beta, in fact, is of two types, beta emissions. One is a beta minus decay, which consists of an electron plus an antineutrino, or a beta plus or a beta positive decay, which consists of the antiparticle of an electron, which is a positron, plus a neutrino. This is always a combination in which they are liberated. Although, remember, the beta plus decay is outside the scope of your syllabus. So I will ignore it and not talk about it for the rest of the session. I'll only talk about the electron plus the antineutrino. In fact, I'll even only mention the electron in passing, ignoring the antineutrino as well, because you do not have the antineutrino studied as elementary particle. So the antineutrino, although yes, it does not contribute to any mass nor charge, it's the electron which contributes to a charge of -1e. So the relative charge of beta particles are -1e. Gamma rays are pure photons of the electromagnetic spectrum. In fact, you've learned the electromagnetic spectrum in order of increasing frequency. It is radio waves, long range, and then short range radio waves, and then microwaves, and then you have the visible spectrum, and then you have infrared, and then you have the visible spectrum, and then you have ultraviolet, and then you have X-rays, and then last, the ones with the highest frequency are called gamma rays. These are just pure particles of light, also called as photons. Pure particles of light, also called as photons. Since particles of light or photons do not carry any charge, their relative charge is 0. Mass, please remember, the mass is 2 protons plus 2 neutrons, giving you a total mass of 2 times atomic mass unit from 2 protons plus 2 atomic mass unit from 2 neutrons, giving you 4 atomic mass unit, which is very, very, very high. In comparison, it's just an electron, which is 0.0005 atomic mass unit, very less when compared to that of alpha particle. Gamma rays or pure particles of light called photons, which have 0 mass. They do not have any mass at all. Speed, their speed can be up to 0.1, that is 10% of the speed of light. These guys can reach speeds up to 90% the speed of light. These travel exactly at the speed of light. Ionizing effect, simple. What is ionizing effect? Let's understand what is the property of ionization. The property of ionization is just the ability of a particle to create ions. Ions, when I say ions, I mean this. Na plus, Cl minus, Fe2 plus. Basically knock out the outermost valence electron from an atom, or the ability to provide electrons to complete the outermost orbital out of a atom. That is the property of ionization or the ionizing effect. Because alpha particles have the highest charge, as you can notice here, they have the highest charge, they have the highest or the strongest ionizing power. Beta particles have a moderate value of charge in terms of magnitude. We don't care about the negative sign. Only by looking at magnitude, it's exactly half as that of an alpha particle. So because they have a moderate charge, they have a weak ionizing effect. Because gamma particles practically do not have any charge, they are very, very weak. It's not 0, remember, because you can still use pure energy to ionize atoms. It's just that the ionizing effect that they have is much, much, much weaker when compared to that of alpha or beta particles. Now let's talk about the penetrating effect. If you remember, the previous diagram did speak about that. Alpha particles look to be the heaviest of all the particles we speak of. Because they're the heaviest, this directly contributes to their penetrating effect or their penetration. They have the lowest penetrating effect. The lowest penetrating effect of all the 3 radiations or all the 3 particles. They have the lowest penetrating effect owing to the fact that they have the highest amount of mass. A thick sheet of paper or even skin or a few centimeters of air is enough to stop alpha particle emission. Or in other words, they can only travel a few centimeters. Few centimeters. Lowest means they can only travel a few centimeters. If you look at the mass of a beta particle, it's still present, it's not 0, but it's much, much, much lesser. It's in fact 1800 times 4. That is exactly 7200 times, or approximately, I would say, 7200 times much lighter, I would say, when compared to that of an alpha particle. So its penetrating effect is moderate when compared to that of an alpha particle because it has much lower mass. It can travel a few centimeters, but a few millimeters of a solid object such as aluminum or any other metal will stop, or it can travel a few meters in air. A few meters in air, or a few millimeters or a few centimeters even through a solid or a metal. The gamma rays are basically pure particles of light called photons, which have basically zero rest mass. Because they have zero rest mass, they have the highest penetrating power of all the three emissions. Because they have the highest penetrating power, they can completely never be stopped. Although, yes, materials such as lead and thick concrete will reduce the intensity of gamma radiations. If you've ever noticed the Chernobyl nuclear reactor, post the radiation disaster that occurred there, the entire reactor is walled by a thick, very, very, very thick, in fact, layers of thick walls of concrete, so as to not allow the radiation to escape into the surrounding atmosphere. They can travel through hundreds of kilometers, hundreds, if not thousands, hundreds of kilometers in air. They can even pass through solids. Some solids, such as lead and concrete, can block radiation or can reduce the intensity of radiation. Effect of fields. When I say fields, we talk specifically about two types of fields, electric and magnetic. So the rule of deflection by an electric or magnetic field is very simple. If your charge, if you have charge, but if your value of charge is not zero, you get deflected by electric or magnetic fields. Alpha particles we've discovered, they do have a charge of plus 2e. So yes, they will be deflected by both a magnetic and an electric field. Beta particles, do they have charge? Yes, they do have charge. Because they have charge of minus 1e, they will get deflected by both magnetic and electric fields, although the deflection occurs in the exact opposite direction as it does for alpha. Why? Because of the polarity of the charge. It's not about magnitude, it's about the polarity. Also, in an electric field, they get deflected in a straight line, or force is linear. In a magnetic field, force is centripetal, which means they'll get deflected in a curve. So when they get deflected in a curve, remember, beta will get deflected more than alpha. So your question might be, why is beta getting deflected more than alpha? The simple reason why beta can be deflected more than alpha is because the charge to mass ratio of beta is far, far higher than that of alpha. Because of this charge to mass ratio, beta, even though has a lower charge and the lower mass, much lower mass, will get deflected more than alpha in a magnetic field. Electric field, they'll both get deflected in opposite directions. Next, gamma particles have no charge. That is, the amount of charge they contain is equal to 0, which means they will not get deflected by either a magnetic or an electric field. So this is a comparison of alpha, beta, gamma in terms of their ionizing effect, their mass, their speed, the relative charge carried, the penetrating effect, and the ability to be deflected by electric and magnetic fields. Please take a look. Okay, fine. Now, we also need to understand what background radiation is. But before we move to background radiation, I need to explain how reactions are written for alpha, beta, and gamma radiations or emissions, let's say. So let me start with alpha first. Alpha is very simple. Alpha, let's take an element X with atomic mass A, atomic number Z. If it undergoes an alpha emission, it will become a completely new element Y. That is because its atomic number will reduce by 2 and its atomic mass will reduce by 4, giving a particle known as an alpha particle or an equivalent helium nucleus, along with the emission of energy as well. Next, what about beta radiations, beta emissions? For beta emissions, the same element X with atomic mass A, atomic number Z, when it undergoes a beta decay, it becomes a completely new element Y with atomic number Z plus 1. I'll tell you why. Atomic mass A. That's because it releases a beta particle, which is basically an electron, atomic number -1. This and this balances with this, and atomic mass 0, because it's practically almost 0. With gamma radiation, the element X, which is in an excited state, will undergo radioactive decay to become a stabler version of the same element, because gamma radiations do not have any atomic mass nor any atomic number, the gamma particle specifically. But pure energy is released in the form of electromagnetic waves, specifically high energy or high frequency, high energy, high frequency gamma rays. Gamma rays. Even in beta radiation, yes, energy is released. It's not that it's not. So this is the comparison of alpha, beta, gamma in terms of the reactions statements written. Next, let's understand what is background radiation. As the word suggests, the background radiation is a small amount of radiation that is present around us all the time because of the radioactive elements in our environment. So you might ask the question, what do you mean radioactive elements? Remember, it is possible for us, it is possible to have trace amounts of radioactive nuclei within the normal nuclei all around us. For example, the banana that we consume has a radioactive isotope of potassium, which is present in every single banana that you ever eat. The fact or the matter of fact is that it's just present in such a trace amount, and the amount of radioactive decay or the background radiation it produces is so small that it is practically ineffective of causing any sort of temporary or permanent damage to any biological specimen around it. That's it. It's not only food, particles of soil, rock, air, drink, even space also contain background radiation. In fact, the background radiation in space is given a special name. It's called the CMBR, cosmic microwave background radiation. These are one of the key, CMBR plays a key role in helping us understand, formulate the concept of the Big Bang, which we understand to be the start or the origin of our universe. We will talk about it more when we go to space physics, which is the last chapter. Now, moving on. Now, here you have a Geiger-Müller counter. Now, what's a Geiger-Müller counter? A simple Geiger-Müller counter is a or a counter is a device that is used to measure the amount of radiation that is present. How do you measure it? Simple. Let's say here I have a source which is nothing but a radioactive material. Radioactive material. Remember, the radioactive material is capable of undergoing radioactive decay. It produces 3 types of emissions: alpha, beta, and gamma. We've discussed that all 3 alpha, beta, gamma have some sort of an ionizing effect. They do have some sort of an ionizing effect. Alpha has the highest, beta has a moderate amount of ionizing effect, and gamma has the lowest. Yes, true. But they all do have an ionizing effect. And when this radiation is incident through this vacuum chamber, which initially passes through a mica window to make sure that there is to filter out. The mica window is just to filter out any other particles, any other unnecessary particles. Yeah. So apart from the gamma radiations or the alpha, beta, gamma radiation, nothing else enters through the mica window. Every other particles is filtered out. This basically makes it a vacuum chamber. And this vacuum chamber consists of an anode here and a cathode. So what happens is, remember, this is initially a vacuum chamber, which is then filled with a gas one of the non-reactive gases, such as argon, for example. So now, when argon is present in this, or molecules of argon are filled in this vacuum chamber, and the radioactive emission, that is alpha, beta, gamma, are allowed to be incident, all three of them, alpha or beta or gamma, are capable of ionizing this argon gas. And when they ionize this argon gas, the ionized particles, ionized gas molecules, get collected at either the anode or the cathode. And when they get collected at the anode or the cathode, they basically, what do? They basically produce a current. They produce a current. So this current is an indicator of amount of radiation produced. Greater the amount of alpha, beta, gamma radiations, greater the ionizing effect, greater the argon ions produced, which means greater the amount of current generated, which in turn means the greater the amount of radiation that is passing through or incident here. You have a rate meter which is able to convert the current measured into the amount of radiation. And this is how you can measure the amount of radiation, whether it is in a particular background environment or due to a particular source, an actual source, not just the background radiation. All of them can be measured using this Geiger-Müller counter or the Geiger-Müller tube. Next, let's understand what is radioactive decay from a nuclear perspective. So let's take the example of radium. So radium is a nucleus. When it undergoes alpha decay, it loses 2 protons, 2 neutrons, becoming a radon gas and giving away an alpha particle. So alpha particle is also sometimes described to be the equivalent of a helium nucleus, He42, because the helium nucleus also contains 2 protons and 2 neutrons. So this is alpha decay. Next, remember, in beta decay, it's just an electron and an antineutrino. In fact, we don't even mention the antineutrino in most cases. You can continue to do that. Gamma emission is pure energy in the form of electromagnetic waves or gamma rays. The next concept we learn about is the concept of half-life. Let's understand what half-life is. Half-life is very simple. It is let me type it as I dictated to you guys. Half-life is defined as the amount of time taken by a radioactive substance to reduce the 3 things. Either reduce the number of nuclei or the amount of radiation produced, which is measured by a quantity called activity. Activity, the amount of radiation produced, is measured by a quantity called activity. Activity is just the amount of radiation or radioactive emissions given out, or the number of disintegrations per second occurring for a radioactive substance. So half-life can be the amount of time taken by a radioactive substance to reduce either the number of nuclei or the amount of radiation produced to half of its previous or original value. Half of its previous or original value. Please don't say it is the number of time required for the nucleus to decay by half. No. Nucleus cannot decay half or 20% or 30%. A nucleus is either decayed or not decayed. That's it. It's a binary state. Got it? If you have 10 nuclei with you, after one half-life that has produced or that has passed, for that radioactive substance, the number of nuclei will just reduce to half, which is 5. Okay? Don't say that all 10 of them have decayed by half. No. All 10 of them were there initially, out of which, after the time period that is equal to exactly one half-life, half of them have decayed, half of them have stayed as they are. That's it. That's all half-life is. Half-life is, again, activity. We've discovered what activity or discussed what activity is. Activity is the amount of radiation produced. It is measured by a unit disintegration per second, also known as becquerel. Although disintegrations or counts per second, counts per minute, counts per hour are also units sometimes used. If you remember, it's like how for speed, even though the SI unit is meter per second, we also sometimes use kilometer per second, kilometer per hour. Similarly, even though the SI unit is becquerel, which is disintegrations per second or counts per second, we sometimes do end up using different units, such as, let's say, counts per minute or even counts per hour or any other arbitrary unit of time or measure of time. So here's a graph looking at the radioactivity or the amount of activity for a given radioactive material. Notice one important thing here. You'll notice that even as time passes infinitely, the amount of activity can never become zero. This is, in fact, a law known as the law of radioactive decay. The law of radioactive decay just says this. It says that the rate of radioactive decay, is directly proportional to the number of nuclei remaining. Number of nuclei remaining. So what it tells us is, basically, as the number of nuclei remaining will reduce and reduce, obviously, because most of it will get decayed, the rate at which they decay will also reduce, which means the only time the activity will become zero or the number of nuclei will become zero. This basically means that activity or the number of nuclei remaining will become zero only at infinity. Or practically, there will never be a time where activity will finally become zero. But there will be a time, in fact, there's a finite amount of time by which the amount of activity always reduces to half of its previous values. Notice these peculiar points. Initially, the activity was 40 becquerel. It reduced to 20 becquerel in a time period of 8 days. Next, it reduced from 20 to 10 in the same time period of 8 days. 10 to 5 also in the same time period of another 8 days, making us understand that this constant time period, 8 days, 8 days, and 8 days is nothing but the half-life of my radioactive substance. That's all it is. I don't know how I know it's a half-life. It's because the time taken to reduce to half of the previous value is the same every single time. Please notice here, I have not taken background radiation into account. If you want to take background radiation into account, just subtract the background radiation value from each of these areas. That's it. Next, there are two types of nuclear reactions that we primarily focus on. One is the nuclear fission reaction. The other is the nuclear fusion reaction. The nuclear fission reaction is basically the splitting up of a heavy nucleus into two lighter nuclei, along with the emission of a high amount of energy. This nuclear fission reaction is brought forth by a process known as a chain reaction, which is when a fast-moving neutron collides initially with an unstable nucleus, kickstarting the chain reaction. And each reaction of the unstable nucleus, each fission reaction produces multiple number of fast-moving neutrons, which then go and collide with more unstable nuclei, causing more and more and more fission reactions. This sort of a process is called a chain reaction, which is in fact an uncontrolled chain reaction is basically the principle of operation of an atomic bomb. A controlled chain reaction is the principle of operation of a nuclear reactor. Here you can see, with each strain nucleon that is colliding with a uranium nucleus, causing the nuclear fission reaction, there are 3 more nuclei produced, which then collide with 3 more uranium nuclei, causing more and more and more and more chain fission reactions. When this is controlled, you can harness this energy using it in a nuclear reactor. A nuclear reactor has two important components that I'll explain first before explaining the functioning. One is a moderator, the other is a control rod. The moderator's job is to slow down the neutrons. Slow down the neutrons. You're basically slowing down the neutrons to sustain a controlled chain fission reaction. Controlled chain fission reaction. And the purpose of the control rod is to absorb the neutrons, thereby turning on or turning off the reactor. Now, let's explain the working of nuclear fission reactor. So a nuclear fission reactor works on a very simple principle. A nuclear fission reactor has or consists of, let me draw the diagram. This is a nuclear fission reactor, which consists of fissionable uranium, enriched uranium rods, which are present or placed between multiple control rods and moderators, which help again either sustain the control chain reaction or stop and start the reaction. The energy produced is primarily in the form of heat as a nuclear fission process is undertaken. And as the nuclear fission process undergoes, coolant, that is water, is supplied throughout the system, which is then collected as high powered steam, which is then used to rotate a turbine, which then through the process of electromagnetic induction converts it into electricity, which can be stored or transferred from one place to another at a power station. This is the principle of working of a nuclear reactor. If you want me to explain the working, the energy transformation that occur, nuclear energy is converted into thermal, which is then converted to mechanical, which is then converted to electrical. That's as simple as that. Now let's talk about nuclear waste. A nuclear reactor, yes, uses enriched uranium as the fuel. And as uranium undergoes nuclear decay, it does become a slightly more stable yet still radioactive element. But the amount of radiation emitted or given out by this element is not strong enough to be converted into useful form of energy in a reactor. So the nuclear waste, which is still, remember, comparatively highly radioactive, is then stored safely or safely disposed of. Again, some examples of nuclear waste include strontium-90, iodine-131, plutonium-239. These again are capable of causing temporary or irreparable permanent damage to the any sort of biological or organic specimen that they come in contact with, including a human. The process of energy creation in a nuclear fission reaction follows Einstein's energy mass relationship, E equals mc square. Here, a small amount of mass is lost during the fission reaction when uranium converts into two lighter nuclei. This small mass that is lost is then converted into pure energy using E equals mc square relationship. That's how energy is produced. The other type of nuclear reaction that we don't speak of much is a nuclear fusion reaction, which is the exact opposite of a fission reaction, where two lighter nuclei combine to form a much heavier nucleus. Contrary to nuclear fission, nuclear fusion gives out a lot more energy, but the offset is that to kickstart the nuclear fusion reaction, to bring two lighter nuclei closer together, in spite of their strong repellent forces, nuclear forces, you have to employ a tremendous amount of energy. So a tremendous amount of energy is required to start the reaction, while nuclear fusion reactions, once sustained, also produce a much, much higher energy output than consequent nuclear fusion or fission reactions. Next, fusion, in fact, is what produces the energy that sustains the life cycle and the energy output of a star, even a star such as our sun. We will talk about nuclear fusion and the life cycle of a star in much, much greater detail when I go to the next topic. So right now, just remember, fusion is not achievable on Earth, at least according to your textbook, it's not. And nuclear fusion is what acts as the sustenance for the energy production and the life cycle of, and it plays a prominent role in the life cycle and sustenance of any star, specifically our sun, a star such as our sun. Now let's talk about the uses of radioactivity. Radioactivity, it's in the medical field, we use tracers. Tracers are radioactive elements, again, safe radioactive elements, which produce very, very, very small amount of radiation. They're basically injected in a body to help understand the functioning of body organs. They can be used in a plant, in fact, to understand the intake of the fertilizer through the roots, adding a tracer to the soil water. They can detect leaks in underground pipes when they're passed through these pipes itself. So these are the applications of radioactive traces. Testing in cracks can also be done using by allowing strong intensity X-rays or gamma radiations to pass through solids. It is just that wherever there is a crack, the X-ray or the gamma ray that is passing through specifically will reflect and refract as it passes through the small boundary region that is produced. And by measuring the amount of, by measuring the received rays to the specimen, you can test the crack. You can not only test for cracks, you can even predict the size of the crack and its dimensions as well. You can even use radioactive radiations for thickness monitoring. As we all know, the penetrative power of different gamma, alpha, and beta radiations is different. So by using a simple beta source, which is calibrated at a certain thickness, let's say, you can measure and monitor the thickness of a material. Carbon dating is one other process where by measuring the amount of radioactive carbon-14 or C14, which is an isotope of carbon that is present in a biological specimen, such as a plant or a tree, you can predict the life of, or the time that the time it would have taken for the biological specimen to form. This is because we know the standard value of carbon-14 concentration that should have been present in a biological specimen when it was formed and when it was alive. By measuring the amount of carbon C14 concentration present currently as it decays to the initial concentration of C14, you can measure the time interval between the radiations, or between the start of these radioactive decay radiations. Again, it helps that you know the half-life of C14 or carbon-14. Next, the atoms and particles. One of the models that we discussed is the Thomson's plum pudding model, where he assumed that the positive and the negative charge particles were spread throughout the atom, which now we know as false. The actual structure is, again, the standard model that we've learned. The Rutherford's nuclear model. Again, Rutherford's experiment helped us conclude a few important aspects. I'll explain what each of them are. I'll explain the observations of Rutherford's experiment and what were the implications of the same. So I'll explain the premise of Rutherford's experiment. The premise of Rutherford's experiment is very simple. He got a thin layer of gold foil, almost a layer made up of a single layer of molecules, which are again attached to each other in a lattice structure. And he allowed an alpha source to pass through this thin gold foil. Why specifically alpha source? Because alpha source is made up of alpha particles which are positively charged. As you all know, the gold foil is also contained, or does also contains gold nuclei, which are also positively charged. So what's the experiment, or what were the observations in the experiment here? I'll start one by one. The first observation was that most of the alpha particles passed through without any deviation. This basically tells us that most of the atom, the implication or the understanding from this observation is that most of the atom is in fact empty. What was the second observation? Second observation was a small percentage of alpha particles were deflected by large angles, which basically means that the gold atom contains a strong and dense positively charged center. By the way, Rutherford at that time did not know what to call it or what it was called. We now know it's called the nucleus, made up of protons and neutrons, which is what gives it the positive charge. The third observation, an even smaller percentage of alpha particles completely deflected or completely retraced their path, which is basically proof that the center is strongly positive. So I think I have to remove the word positive from this part. A dense positively charged center. The fact that it was strong was understood from this third observation. So these are the observations or the inferences from observations and their inferences, I'm sorry, corresponding inferences of the Rutherford scattering experiment. Again, here, most of them of about 95 to 97% undeflected, a small 2-3% deflected by large angles, an even smaller percent, that is 0.01 something percentage, deflected or retraced their path, such that we know that the nucleus is strongly positive. Again, this this just talks about the discovery of the neutrons. After the discovery of the neutrons in 1932, we discovered that the center consists not only of protons but also of neutrons. So this concludes the chapter Atomic and Nuclear Physics. Our last session will be on the topic that is space physics, where I will try to complete or give you a brief understanding of all the processes that occur or that occur, whether it is to a star, understanding Earth, the rotation of the Earth about its own axis, the revolution of the Earth around its own axis, the rotation of the Earth around its own axis and the revolution of Earth around the Sun and other cosmic events and entities. Thank you for your time, guys.